Okay, let's dive right into this explainer and demystify the invisible shield that protects, well, basically our entire online lives. Think about it. Every single day, whether you're firing off a private text message, buying a coffee through a mobile app, or logging into your highly sensitive bank accounts, there is this silent, deeply complex mathematical system operating right beneath your fingertips. And most of us never even notice it. So today we're going on a quest. We are going to uncover exactly how cryptography actually works, breaking down the seemingly magical math that literally keeps our entire digital world from just collapsing into total chaos. Now, to really appreciate this, we have to start with the ultimate problem we're going to solve today. And honestly, the answer is absolutely fascinating. I want you to picture the internet for a second, but don't picture it as some safe, secure pipeline. Picture it as a massively crowded, incredibly noisy room where absolutely everyone is listening in on everything you say. So if you want to slide a highly confidential, locked steel box across this crowded room to someone you've never even met, how in the world do you do it when you can't securely hand them the key? That incredibly tricky puzzle is what drives every single thing we're about to explore. So here is our roadmap for the journey. First up, we'll establish the language of secrets. Then we'll look at the shared secret key method. After that, we hit a massive roadblock called the distribution problem, which leads us to the brilliantly clever two-key solution. And finally, we'll see how it all comes together in the modern hybrid approach. All right, let's kick things off with the language of secrets, because before we can look at the complex systems, we absolutely have to get our basic definitions straight. Let's start with what we call M, or the message space. This represents the original, completely unencrypted strings of data that you actually want to communicate. Think of this M as your clear text or plain text. It encompasses everything, every single readable email you write, every raw photograph you take, every unhidden password you type. This is the stuff you want to send across that crowded room we talked about. It is your totally vulnerable data in its most naked form. But once you protect that data, it enters a whole new world. It enters C, the ciphertext space. If you look at the visual representation here, like an armored transport vehicle, you get the idea. Your message no longer looks readable in any way, shape, or form. It becomes a completely meaningless, disorganized string of random bits to any eavesdropper who happens to be looking. To anyone without the proper access, that original message is entirely impenetrable. And that brings us to the actual locking mechanism itself. The strength of this entire system relies on a key, and that key is pulled from K, the key space. I want you to imagine a massive, almost infinite universe of every single conceivable password or cryptographic key. The absolute cornerstone of security here is that your specific key must be chosen uniformly at random from this vast space. Why? Because if there's even a pattern, if it's even slightly predictable, the bad guys will guess it, and the entire shield fails. It has to be totally random. Now check out the mathematical symmetry here, because it's pretty beautiful. On the left side, we have the encryption algorithm, represented by E. This algorithm takes your random key, K, combines it with your message, M, and spits out your locked ciphertext, C. It locks the box. Then, over on the right, the decryption algorithm, D, reverses that exact same process. It takes that same key, K, applies it to the scrambled ciphertext, C, and magically pulls out the original readable message, M. Which leads us to a non-negotiable rule called the correctness property. Decrypting an encrypted message must flawlessly, and I mean flawlessly, return the exact original plain text. A single dropped bit, just one tiny error, it means the whole file is corrupted. There is literally zero room for error here. If you lock a message up and then unlock it, what you get back must be, unequivocally, perfectly equal to the original message, M. Okay, so we've got the vocabulary down. Let's move on to our first major tool, the shared secret key, also known as symmetric cryptography. This is the oldest and historically the most common form of encryption out there. Let's say Alice wants to talk to Bob using a symmetric setup. They have to follow 4 specific steps. Step 1, they have to securely agree on a single shared key, K. They both need the exact same key. Once they have it, step 2 is encryption. Alice uses the key to lock the data for confidentiality, keeping all those eavesdroppers in the crowded room out. Step 3 is transmission, where they send it across the network while also checking for message integrity. And finally, step 4. Bob receives it and uses that exact same shared key to decrypt the data. Now, the real beauty of symmetric algorithms, things you might have heard of like AES or Cha-Cha-20, is their blinding incredible speed. They're highly computationally efficient. They can process huge volumes of data fast, like a high-speed conveyor belt.
And to make sure some attacker hasn't messed with the data while it was traveling across the network, they use things called message authentication codes, or MACs. You can think of a MAC like a digital tamper-evident seal on a medicine bottle. It guarantees total data integrity. If the seal is broken, you know not to trust the contents.
But as amazing and fast as symmetric cryptography is, relying purely on shared secrets sets up a massive world-breaking issue for modern networks. This is the distribution problem. Seriously, think about this for a second. How can two people securely agree on a secret key over the internet before they even have a secure channel to talk on? It's a chicken and egg problem. If you want to buy a book from a website hosted on the other side of the world, you can't exactly fly there in person to hand the server administrator a literal flash drive with your secret key, right? In a global network with billions of users, securely distributing unique pairs of secret keys to every single person who wants to communicate is just logistically impossible. The system simply cannot scale. It's a fatal flaw.
And that brings us to the hero of our story, the two-key solution, better known as the public key revolution. This concept completely changes the game and solves our massive distribution nightmare.
So instead of trying to share one single secret key, each user actually generates a pair of keys that are mathematically linked. On the left side of our comparison here, you have the public key. And just like the name says, you can publish this key to the entire world. Anyone can see it, and anyone can use it to encrypt a message that is meant specifically for you. But on the right side, you have the secret key. This one is strictly confidential. Only the owner possesses it, and it is literally the only mathematical tool in the entire universe that can decrypt the messages locked by its matching public key. This is a massive paradigm shift. It means Alice can just look up Bob's public key in a public directory, use it to lock her message, and know with absolute certainty that only Bob's private secret key can read it. He didn't need to send her a secret key beforehand at all. But wait, it gets better. Asymmetric cryptography does something else incredible: digital signatures. Alice can actually run this process in reverse. She can use her private key to sign the data. Bob then uses her widely available public key to verify that signature. This proves unequivocally that the message really came from Alice and wasn't a forgery by someone else in that crowded room. So we have the fast lock, and we have the brilliant two-key solution. Let's see how these systems combine to form the climax of modern internet security: the modern hybrid approach. As you can see on this table, we face an ultimate trade-off in cryptography. Symmetric cryptography wins hands down on pure speed and efficiency, but it fails completely when it comes to securely sharing keys at a global scale. On the other hand, public key, or asymmetric cryptography, brilliantly solves that impossible sharing problem. But the catch? It involves incredibly complex math. It's computationally massive, wildly expensive for your computer's processor, and honestly, it is far, far too slow to do something like stream a 4K video. So what do? We combine them. Modern systems like TLS, which, by the way, is the exact protocol behind that little padlock icon you see in your web browser right now, use a hybrid approach. In step 1, your computer uses the slow, secure public keys just long enough to safely swap a temporary one-time session key. Once that tiny session key is securely exchanged across our crowded internet room, they drop the slow math entirely. In step 2, they switch over completely to that blazingly fast symmetric cryptography, using that new session key to encrypt the actual massive data stream for the rest of your browsing session. It is an unbelievably elegant solution that combines the very best of both mathematical worlds. It's a system we invisibly rely on for every single online interaction we make. But, as we marvel at the genius of this architecture, it does leave us with one final, incredibly provocative thought about the future. If our entire modern web heavily relies on the mathematical difficulty of breaking these public keys, what exactly happens to all our closely guarded secrets when a massive, sudden leap in computing power suddenly breaks that math? It's definitely something to think about the next time you see that little padlock. Thanks for joining me on this explainer.